My name is Jinwook Chang from Shanghai American School Puxi campus.
My name is Talin Patel from Basis Independent Brooklyn.
Today we'll be presenting the effect of cadmium selenide quantum dots on the efficiency of silicon solar cell, a hands-on project-based learning. While studying the introductory material science and nanotechnology course, we encountered the problem with conventional silicon solar cells. The fact that they cannot make use of a powerful solar energy source, the UV light. Since UV light has a shorter wavelength than that of visible light, UV light is unable to excite electrons across most photovoltaics bandgap to generate electricity. After conducting extensive research on the materials that could assist in manipulating the bandgap, we came across quantum dots, nanoscale semiconductor particles that can absorb and emit light due to quantum confinement effects. More specifically, through multiple exciton generation, where one high-energy photon creates multiple electron-hole pairs, and spectral management, where UV light is downconverted into wavelengths silicon can absorb more efficiently, quantum dots help make use of UV light in solar cells. So, in order to test this hypothesis, we conducted an experiment to assess the efficiency of silicon solar cells once quantum dots were applied. And after successful results, which will be introduced later, we wanted to bring the joy of project-based learning to other fellow high school students as high school students ourselves. And that's when we decided to build a high school laboratory module that can teach students complex material science and nanotechnology concepts with available equipment in the high school laboratory through our very own project-based learning module. So, in sum, the motivation behind the study included the need to improve silicon solar cell efficiency using quantum dots and to provide students with an effective hands-on project-based learning experience in applying nanotechnology to real-world challenges.
To begin our experiment, we first characterized a calibrated polysilicon solar cell to create a performance baseline for comparison with the quantum dot coded versions. We used cells from SolarMade and tested them under standardized testing conditions. Using an Arduino-based setup and an ENA 219 sensor, we measured current and voltage, while a 4-point probe setup ensured accurate readings. We then calculated input power by comparing the short circuit current of the testing day to the manufacturer's standard rating. This allowed us to build two curves, an IV and PV curve, as shown in Figure 3. These curves were then later used to compare our calibrated silicon solar cells to our quantum dot enhanced cells. And we didn't just choose silicon-based solar cells because they're available. We chose them for a specific reason, and that was they offered a cost-effective alternative to expensive solar simulators and lab-grade reference cells. By using the manufacturer's baseline data, we were able to approximate standardized testing conditions without needing the high-end lab infrastructure that you would normally need. This allowed us to make this method especially valuable in educational or research-limited settings. The next part of this experiment was synthesizing the quantum dots. We synthesized cadmium selenide quantum dots, which we used to coat the test solar cells. We prepared two solutions, a selenium stock solution and a cadmium stock solution. During the synthesis of the solutions, we combined both solutions at 165 degrees Celsius in a 1-octadecene and allylamine mixture. The aliquots were then taken out at various time intervals to produce different sized quantum dots. Under visible light and UV light, the quantum dots display different colors, as shown in Figure 4A and B, indicating size variation due to different band gaps, as shown in the vials. And the reason why we chose cadmium selenide quantum dots was because, in comparison to other quantum dots, they are less toxic and easier to reproduce in laboratory settings.
So then we moved on to the quantum dot separation and characterization. So during our experiment, we not only wanted to test that quantum dots can help increase the efficiency under UV light, and we also wanted to test that how the different sizes of quantum dots can help the efficiency improve in the silicon solar cells. So figure 5A demonstrates the emission spectra of quantum dots. And this indicates the wavelength of light the quantum dots assist in absorption. As the synthesis time increases, the emission peak increases. And this really indicates how we controlled the different sizes of quantum dots through different quantum dot synthesis time. The figure 5b, the Stokes shift, indicates the differing wavelengths of the emission and absorbance of the light. And here the emission peak is greater than the absorption peak due to energy relaxation of electrons before photon emission. And this picture right here, the Stokes shift, demonstrates the quantum confinement effect of how quantum dots can uh, change or manipulate the wavelength of the emitted light compared to the one absorbed as the peaks are different. So five quantum dot samples with increasing emission peaks from 439 nanometers to 571 nanometers were purified using solvent-assisted centrifugation and redispersed in hexane. And these samples were then coated onto solar cells and dried. So since we're conducting this experiment at a high school laboratory setting, we didn't have access to any of the lithography tools that would have been accessible in university labs. So the way we chose to disperse the quantum dots was to use just to spray and disperse the quantum dots on top of the calibrate solar cells evenly in order to create a layer of quantum dots on top of the silicon solar cells. So figure 6a depicts the quantum dot precipitation, a concentrated volume of quantum dots where there are millions or billions of 2 to 10 nanometer size quantum dots before mixing with hexane. Figure 6b shows our experimental setting with two calibrate solar cells, one without uncoated solar cell, and the one on the right, quantum dot coated solar cell. As we had the privilege to validate the experiment at the Singh Center of Nanotechnology at the University of Pennsylvania, we had the privilege to implement the scanning transmission electron microscopy to test whether we have successfully created the quantum dots through this experiment. And in this 50 nanometer scale image, as you can see, the tiny particles on the figure 6c, we were able to successfully create quantum dots in various sizes. So now moving on to the effective cadmium selenide quantum dots on the efficiency of solar cell and how the results turned out. So figure 7a depicts the IV curve of solar cell with quantum dots under visible light, and figure 7b shows the measured efficiency of solar cell under visible light and UV light. In sum, the standard solar cells showed efficiency of 16.2% under visible light and 12.19% under UV light. Lower UV efficiency led by silicon's poor absorption in the UV range and thermalization losses from high energy photons. The efficiency increased under UV light after quantum dot coating, as the quantum dots converted UV photons into visible light that silicon could absorb more effectively, validating our principles of multiple exciton generation and spectral management. Smaller quantum dots yielded better efficiency, with quantum dots with 439 nanometers emission reaching 13.83%, while quantum dots with 571 nanometers only achieving 11.85%. So in this experiment, the silicon solar cells without the quantum dot coating performed better in visible light, while the quantum dot coated silicon solar cells performed better in UV light. So although quantum dot coated cells showed reduced efficiency under visible light, this is likely caused by the increased surface reflection as we add an additional layer of quantum dots on top of calibrate solar cells. And as the UV light efficiency under UV light increased, um, this demonstrates a successful testing of our hypothesis that quantum dots help the absorbance of UV light for silicon solar cells.
Well, as mentioned previously, this study had two main motivations. The first was to test the efficiency of cadmium selenide quantum dot coated solar cells under both UV and visible light. The second motivation was to test whether this learning sequence was useful in educational settings. In order to test this, we conducted a survey at the end of this experiment. And the survey results demonstrated that this learning sequence program gave students a transformative educational experience. Reports such as "I realized the close link between the theoretical science and real-world applications" demonstrated that this learning sequence was able to bridge in-class experiments to real-world application. Moreover, the second report demonstrated that during this process, team members were able to learn how to work together in a research setting.
Before we end our presentation, I would like to make a special acknowledgement to Dr. Gyusuk Kim at the University of Pennsylvania, the mentor of our research project. He helped us in the experiments at the Singh Center of Nanotechnology and the writing the manuscript process, as well as letting us know of the valuable opportunity to present at the 53rd IEEE Photovoltaic Specialist Conference in Montreal, Canada.
I'd also like to acknowledge the UPenn students and faculty that helped us along our experiments. Moreover, I'd like to thank the students that were unable to attend the IEEE Photovoltaic Specialist Conference, but helped us greatly during the manuscript writing process. To conclude, through the ESAP Nanotechnology program, we not only conducted hands-on experiments, but also connected classroom theory to real-world applications. One key outcome was that coating solar cells with cadmium selenide quantum dots improved efficiency under UV light, thanks to wavelength selective photon conversion. This experiment not only helped us develop lab skills and teamwork, but also helped us understand the importance of project-based learning in STEM. Overall, we saw that even at the high school level, students can meaningfully contribute to applied research in energy and nanotech by integrating synthesis, measurement, and analysis.
Thank you for listening to our presentation, and we look forward to do more great work in the future. Thank you.